Okay, so we just saw this definition of universal hashing, the C approximate version, and also applications of it to different examples. Now we're going to try and look at concrete implementations that are actually efficient, much more efficient than doing a truly random hash function. And the example that we're going to look at first, I think it fits here. Let's put it. It's called multiply mod prime. It's typically the name for it, so let's call that. Multiply mod prime. So here, the idea is to say, pick a prime. And so this is for hashing integers. So here we're assuming that the input domain, let's say here, right? So the universe here is all the integers from 0 to u minus 1. So we just need to pick a prime that is greater than or equal to u. The numbers are from 0 to u minus 1, so we need a prime that's at least. So this prime doesn't have to be random, it could be any prime. Pick an arbitrary prime like this. And now to draw your hash function, this is the random part here. So pick A uniformly in this range that I call PE plus. So this is the set of numbers 1 to P minus 1. Pick B independently of A and uniformly in P, like this. So these are the two random choices that you're doing when you're picking your hash function. And now your hash function is just the single hash rate. Rather simple one, let's write hash of with AB as the random choice. If I want to hash X, what I do is I do A times X plus P, mod this prime P, and then I do mod M. And so the last mod M is hashing it down to numbers from 0 to minus 1, the output domain of our hash. So we do two mod operations, but it's basically take your X, multiply with A, add the B, do modulo the prime, and then do modulo this M. So the nice thing here is that if you're hashing, let's have an example where the universe we're hashing now is the set of numbers from 0 to the 64 minus 1. Best thing hashing 64-bit integers is a simple unsigned integers is a nice example to have in mind. Then yes, the prime, pick it larger, or at least 2 to the 64. So pick some prime that's at least 2 to the 64. There's some theorem saying that there's always a prime between u and 2u. So you can have a prime p that is, say, just to get an idea of how big are these numbers you're picking. You can find some p between 2 to the 64 and 2 to the 65. So it suffices with 65 bits to describe it. Similarly, so your number A, number from 0 to P minus 1, so 65 bits are also enough here, and 65 bits are enough for picking B. Right? So it's very few numbers you have to store. Like I guess in a typical programming language, maybe you store it two 64-bit numbers or something like that. Right? So it's very few numbers of bits that you're using in storing the random seed, particularly compared to if I had a truly random hash function, I just had to store a random number for every element in the universe, right? This is much, much fewer bits. No problem at all. Just storing these two numbers, A and B. The tricky part is, of course, proving that this hash function is universal. And we'll actually prove something even slightly stronger, which might be surprising. We will prove, show here, so this is kind of like our goal, is to prove that for any x not equal to y in our universe U, it holds probability, and here the random choices are A and B, right? This is what we choose. The probability that this hash function applied to X is equal to this hash function applied to Y is actually, and this is maybe a little surprising, strictly less 1 over n. And this holds for, and I guess we're going to assume that the universe is larger than n, and we're hashing to more than one entry, because if we're only hashing to one entry, everyone gets the hash value 0 anyways in the situations. So maybe it's a little bit weird, because if I had a truly random hash function, the collision probability would be exactly 1 over n. What we're saying here is you can actually do a little bit better. You can actually have a collision probability that's strictly less than 1 over n. It might be a little surprising. It's not much less, just to know, but it is actually strictly less than 1 over n. We'll see why. But this is our goal. So this is a universal hash function. And so to prove this, I guess we need some, a little bit of number theory, not much. So we're just going to use one fact. Prime P and what should we call them? I don't want to call them X and Y, or maybe I can let's call them alpha and beta. Alpha, beta in P plus, so non-zero elements. So this was this range from 1 to P minus 1. If I pick an alpha and a beta that are non-zero and less than P, then alpha times beta is not congruent to 0. This is a property of primes, that it's a finite field. You cannot take two non-zero field of whose prime together and get 0. That's basically what it means. I hope you saw this in some games. It's a simple property. You cannot take two non-zero numbers, less than P, multiply them together and get 0, 1. So this is basically the fact we'll be using to try and establish this. Oh. So let's try. So the idea is, so we want to prove something for all x not equal to y. This has to hold. So let's just let's say fix x not equal to y. It's just an arbitrary pair, x not equal to y. Fix x not equal to y. Means that both x and y are less than by choice of p. Okay. So the key now to try and analyze what happens now. Now I'm looking at, I have this fixed x and y. I want to see what is the chance that they now hash to the same when I draw my a and b. Now this is what we have to analyze. So the idea here is to so what does the hash function look like? Right? It has ax plus p mod p mod n. We'll start out by trying to understand what is happening in this hash function before we do the mod n. So let's try to just figure out what is happening in this part. And then we can handle the mod m part at the end. So let's try to understand what happens before I do the mod m when I'm only doing the mod p. So here we're going to, for such a pair x and y, and for a choice of a, b in the hash function, we're going to define two numbers. Or let's say them a, b. It is a pair where a, technically we're choosing a in p plus, but for now let's just try and look at a general definition where they can both be anything from 0 to p minus 1. And we'll see that excluding the choice of a 0 only helps at the end. Okay? Intuitively, why does it help if I don't pick a equal to 0? Well, whenever I get a equals to 0, right, then the hash value of all the elements is just b mod prime mod n. So everything hashes to the same if a is 0, right? So it makes sense to not choose a equals to 0. But for now, let's just look at an arbitrary pair ab. And for such an ab, let's look at two different numbers here. Right, so we're going to look at the numbers q and r such that ax plus b is, let's write it like this is all equal to q mod p, and ay plus b is equal to r mod p. Right, so basically what I'm saying is, as soon as when I choose my a and b, this gives a value of ax plus b and a value of ay plus b. Right, so these are kind of the values that I would get if I only did mod p. If I didn't do the last part of the hash function. Right? We would like to try and argue something about what do these pairs Q and R look like for different A's and B's, and so on. Oh. So we kind of have a claim here that we would like to try and prove, and this is going to kind of be useful in our analysis of this part here. So the claim that we'll try to argue is that, right, like this, there is a bijection between, say, these pairs AB and QR. So what does that mean? It means, I guess, that if you look at all the possible AB pairs, all the possible QR pairs, and which ones go together, then it's I guess everyone on one side has one partner on the other side, right? So clearly, for any choice of AB, there is one choice of QR. That kind of makes sense here, right? Because as soon as I pick my A and B, I get two values of Q and R. What I'm saying is that you cannot have, I guess, two distinct pairs, AB and A prime B prime, that gives the same QR pair. This is what we want to argue, right? So you get distinct pairs. Kind of makes sense. The number of AB pairs is P times P. The number of possible QR pairs is also P times P. Could make sense that this bijection between them, right? So every AB pair gives a distinct QR pair. So let's try to argue that this is the case. Okay, so maybe let's do it here. So I think maybe the easiest way to see this is kind of maybe assume that you have two pairs, AB and A prime B prime, that gives the same QR. Let's try to assume we have this, and then we're going to conclude that they must be equal. So let's say AB and A prime B prime gives same QR. We want to prove this implies A and B prime. This is what we want to argue. So what can we do? We know that these pairs satisfy these equalities here, right? Definition. So we can start by subtracting one inequality from another. So they must also satisfy. If I subtract this one from that one, and what is left, the b's cancel out, right? So then I get something that says A times X minus Y is, I guess, maybe we say it's equal to Q minus R. Maybe it's congruent to Q minus R mod B. Right, so this is by subtracting them from one another. I can do the same with A prime and B prime. Then I get A prime X minus Y. It's also congruent to Q minus R mod P. Right? Then I can subtract these two from one another. Then I get A minus A prime X minus Y is congruent to 0 mod P. Okay. But what do I have now? We're looking at distinct X and Y, right? We have a distinct pair X and Y. So this is a non-zero number mod P. This is not 0. So we can now use our fact, right? If this is non-zero and I'm getting 0 afterwards, the only way that can happen is if this, you cannot have two non-zero numbers that is congruent to 0 mod P. Their product is congruent to 0 mod P. So this implies this difference is 0, so that means that A prime has A prime A. So if I have a pair that give the same QR pair, then A prime and A have to be the same. Let's also argue that now that B and B prime have to be the same. I guess for that one, I guess we're starting with, let's look at this equation here, and we're going to subtract it off for the A prime B prime pair for the one from the AB pair. Okay. So the nice thing now is we know that A prime equals to A. Right. So when I get AX minus A prime X plus B minus B prime, and then I subtract Q from Q, then I get it's congruent to 0 mod P. A prime and A are the same, so these kind of cancel out, and then I get B minus B prime is congruent to 0 mod P. Since they're both numbers between 0 and P minus 1, they have to be. So also B prime. So this establishes this fact, right? There's this bijection between this pair, these B's and Q and R. So let's maybe do one more observation. That so if so again we're kind of excluding these pairs where A is 0, right? When we're actually picking our hash function, we're picking A from 1 to P minus 1. Let's see what difference does that make. What are the pairs Q and R that correspond to this? So let's try to look at what happens when A is 0. What will we get? When A is 0, basically we get that Q and R, right? This is exactly what we get. Q becomes equal to R. A equals to 0, we get Q is equal to R. Okay. So now if we're a little careful, we can see how many pairs AB are there where A is 0. There is exactly P pairs, right? One for every choice of P. How many pairs are there where Q is equal to R? It's exactly P pairs. So basically what I'm saying is that if we pick A not equal to B, basically we have an A not equal to 0, sorry. I could write like this, when A is in this P plus, then we have a bijection between these, and pairs Q are Q not equal to R. Make sense? Basically, because all the pairs where Q is equal to R correspond to pairs where A is equal to 0. There's equally many of them, and it was a 1-to-1 correspondence. So it also means if I exclude the pairs where A is 0, I get a bijection between these pairs and the pairs of Q and R where Q is not equal. Oh. That's also so useful now, in particular when we want to bound this probability. This is basically to show the strictly. So what do we know now? We know we pick our A and B uniformly and independently in these ranges. That also means, because we have this 1-to-1 correspondence, that the corresponding pair Q and R is going to be uniform random amongst all pairs where Q is not equal to R. There are equally many of them. It's bijection. So the pair Q and R is going to be uniform random amongst all pairs with Q not equal to R when we draw our A and B. So now we understand basically the hash function, the blue part of the hash function. Before we do mod M, we understand this hash function. Get actually an independent pair of hash values among all the possible pairs where the hash values are different. Make sense? So the last part is now to just understand what happens when we now do the mod M at the end. How does that change things? So the only thing left is the mod M. Now we're doing mod M. We want to bound this collision probability, and we know the pair Q and R are uniform random among all pairs of Q not equal to R. So basically, we would like to count now how many of these pairs cause a collision on it. Because there's uniform random among all these pairs, it's sufficient for us to understand how many of the pairs cause a collision. Okay, so what we're going to say is we're going to say, okay, let's look at all the possible values of Q and count how many values of R cause a collision when I do mod M. Make sense? So we're going to look at all choices of Q. For every choice of Q, P such choices. Choices. Let's count how many choices of R cause a collision. Okay. So how do we do that? So we're doing mod M, right? And this number here lies between 0 and P minus 1. Maybe one way to visualize it is, let's try to draw all the numbers maybe stacked kind of like this. I think maybe a reasonable way to move the number 0, 1 up to P minus 1. When I'm doing mod M, what is intuitively happening? Kind of like, okay, for the first numbers from 0 to M minus 1, I basically just get the number 0, 1, 2, like this, right? Then I'm going to do another stack of 0, 1, 2, up to M minus 1, and so on, 0, 1, 2, and maybe the top one, M doesn't divide P, because P is prime. So at the end, I'm not going to get a full stack, if you will, of possible values. But this is what when I do the mod M, this is what I get, right? If I have my number from 0 to P minus 1, and it's going to, I'm going to do mod M, and I'm going to get this value that is written here. So for every choice of Q, let's define I as the number so that so I is let's say I is Q mod M. So there's some value I, and now which choices of R, or how many choices for R is there that cause a collision? Well, I'm only going to get a collision when I do the mod M at the end, right? I'm doing mod M over here. I'll only get a collision if R is also I mod M. Exactly what I'm up. So how many such values of R is there? Well, there is at most one in every bucket except the last one. Every bucket has one except the last. Maybe the last one has one, maybe it doesn't. Does that make sense? So there's at most one in here, maybe one in the last one. Okay. So, and also, we're only looking at pairs Q not equal to R. So, how many choices are there? Choices of R causing collision. Well, it is less than equal. Okay, so how many buckets are there? Well, there's P divided by M rounded up. You can convince yourself of that. I think it's, yeah, so P divided by M rounded up buckets. And one of them is where Q is, so that one does not cause collision. So this is the number of choices of R that cause collision at mode. And let's try to upper bound this. So here's a nice kind of trick for handling ceilings when you want to, if you want to get rid of this rounding here. So you can prove that this is, whenever I'm doing integer division by some M, you can get rid of the ceiling and say it's less than equal to P plus M minus 1 over M. And it's still a minus 1. Why is that the case? Well, I think, okay, so maybe one way to see it, if I can draw it down here, is if I look at what is P divided by M, there are the integer values, and then it's kind of divided into little pieces of length 1 over M here. So the value is some integer multiple of 1 over M, dividing P by M. So it's going to lie somewhere. If it lies exactly at an integer, the rounding doesn't do anything. If I lie anywhere, then I'm going to stay in this value. If I lie at any of these positions, I'm going to round up to the next integer here. Make sense? And so you can see the biggest difference between your value and what you round to. It's not a full integer 1. It's a little bit less, right? Because you actually have to start at least a 1 over m fraction into the next integer when you're rounding it. So this, the amount of stuff that you're adding here is at most m minus 1 over m. Does that make sense? So this is why this rounding adds at most m minus 1 over m to your value. It's actually important if you want to prove that exactly. The formula that we have over there, this minus 1 is actually important. Okay, but it's just to get really tight bounds. So this is the number of collisions, and I guess we can write this minus 1 as m over m. I just put them on a common denominator, so m over m, and then we get p minus 1 over m. This is the number of choices of r that cause a collision once I've fixed the choice of q. Right? So how many colliding pairs are there in total? Well, there are p choices of q, and for every one of them, there's p minus 1 over m choices of r that cause a collision. So there's less than or equal to p minus 1 over m pairs that collide. I'm choosing my a and b uniformly at random amongst p times p minus 1 values. Right, so the chance I get a collision is this divided by p times p minus 1, and you get 1 over m. So this proves with a normal inequality, not a strict inequality. Why can you also get a strict inequality as I claimed over there? It is basically because there has to be at least some choice of q where there's not p divided by m rounded up many choices, but of r, but there's only p divided by m rounded down many choices. There's at least one choice of q, so there's at least one choice of q with less than or equal to p over m rounded down minus 1, and this is strictly less than p divided by m rounded up, because p is prime, so m does not divide p, so these two numbers are different. So there has to be at least one choice of q where you get less than or equal to this many pairs. So the total number of colliding pairs is strictly less. So this is just to handle this last case and show you can actually prove collision probability is strictly less than 1 over m. So this shows that for this multiply mod prime, you can actually show that this has this universal property even with a strict inequality. Nice. So I think maybe this is a good time to